Yes, children, we have seen the number of atoms present in primitive cubic cell. Next, what is the second subdivision? Body-centered cubic unit cell. In this, how many atoms are present? That we are going to see now. See, body-centered cubic unit cell, it is in short represented as BCC. What is BCC? Body-centered cubic cell. This has got atom at each of the corner and one atom in the body center. While primitive cell has 8 atoms, correct? While body-centered cubic unit cell has one atom at each of the corners. It is having one atom at each of the corners and also one atom which is present in the body center. Now, how that 8 corners are represented? 8 corners into 1 by 8 per corner atom into 1. So, one body-centered atom will have 1 into 1. You know how you obtained this one? 8 into 1 by 8 into 1. Okay. So, 8 into 1 by 8 is 1. So, 1 into 1 atom. So, the total number of atom per unit cell is equal to 1 plus 1, that is 2 atoms. So, what is the total number of atom which is present in BCC? It is going to be 2. What is the total number of atom which is present in primitive cubic cell? It is 1. Okay, done. Moving to face-centered cubic unit cell. What is the short form? FCC. What is the short form of BCC? I mean, body-centered cubic cell is represented as BCC. Face-centered cubic cell is represented as FCC. Now, face-centered cubic cell contains 1 atoms at all the corner and it has got center and all the faces of the cube. So, when you see that is in a face-centered cubic unit cell, you have 8 corner atom into 1 by 8 per unit cell, which is equal to 1. This first step will be coming same from primitive unit cell. And what is the second step? Since it has got 6 face-centered atom into 1 by 2 atom per unit cell is equal to 6 into 1 by 2, which is nothing but 3. So, what is the total number of atom present? It is 3 plus 1 atom, that is 4. So, in primitive cell, 1 atom. In body-centered cubic cell, you have 2 atoms. And in face-centered cubic unit cell, we have 3 atoms present. Now, this is an example, or this is a structure for face-centered cubic cell. Next is packaging. See how to package the atom in these unit cell. Packaging can be done in 3 ways. Like either you can do the packaging in 1 dimension or 2 dimension or in 3 dimension. Okay. In that first one we are going to see is close packing in 1 dimension. From this picture only you are able to get the clear idea. I am going to pack the unit cell in such a way such that it should be done in 1 dimension. Okay. Let us see the theory. See, there is only one way of arranging the spheres in 1 dimension. Correct, no? How will you arrange a sphere? If I am going to give you 6 to 10 balls, the only way to arrange will be in 1 dimension. That is, you will be arranging them in the way of a straight line. Now, this is the only way to arrange the spheres in 1 dimension close to packed structures. You need to arrange them in a row such that they touch each other. Correct, no children? If I am going to give you a square or a triangle, there are various ways. There are probability like you can arrange them in various ways. But as far as spheres is concerned, there is only one way. You need to pack them in such a way such that they are in the form of a row. They should be touching each other. And when you see this arrangement, each sphere is in contact with the 2 of its neighbors. Am I correct? See the second sphere, it is in contact with first and third. See the third sphere is in contact with 2 and 4. So each sphere is in contact with its 2 of the neighbors, that is left hand side 1 and right hand side 1. So the number of the neighbors of that particular particle is called as a coordination number. Like how many neighbors I have to touch with, they are going to call them as coordination number. So here what is the coordination number, children? In 1 dimension it should be 2 because I have 2 neighbors, one in the left and one in the right. So the number of neighbors will be 2 for packing in 1 dimension. Okay, clear. Now 2-dimensional packing. I'll be showing you the picture. Let me explain the theory first. What is 2-dimension packaging? When 2 rows are combined touching each other, then you will be getting a crystal plane. Okay. See, this is how. when I am going to arrange the two rows together, then what children I'll be getting? I'll be getting a crystal plane. This row combination can be done in different ways. What is the first way? See, when the particles are placed such that they are in adjacent rows, then it will be horizontal as well as vertical alignment, and they'll be forming square. This is called as square close packing. So, how will I arrange rows? There are various ways. First way how I have arranged, I am going to place adjacent rows. In that case, either horizontal or vertical alignment, so they will be forming a square. This is called as square close packing. Now I am going to call row first as A type. Second row is exactly same as the first one, so that is also A type. Similarly, I can place more rows like this A type of arrangement. So you understood? Row 1, then row 2, then row 3. Like that I am going to stack them. Clear? Because all are identical, all are having spheres, so I am going to call them as row 1, I mean row A, row A, row A. So I have now 3 rows. I am going to arrange the 3 rows such that I will be getting a square. So this is called as square close packing, SCP, square close packing. Now see, in this arrangement, if I am going to stack one above the other, then one sphere or one particle is in contact with 4 of its neighbors. So here what is the coordination number, children? The coordination number will be 4. Okay, I am in the center. Now before, what did I tell you? I am in contact with the 2 of the neighbor. One fellow is in left hand side and one fellow is in the right hand side. Now when I am going to stack the rows one above the other, then what happens? I, being a sphere, will be in contact with 4 of my neighbors. How come it is? Left hand side, right hand side, top and bottom. So I have 4 neighbors around me. So what is my coordination number? My coordination number should be obviously 4. So here the coordination number is 4. Also, if you see the center of the 4 immediate neighboring spheres, they are joined, and as a result a square is formed. So this is called as square close packing in 2 dimension. Okay, I have explained very well about one dimension. There is only one possibility. You have to arrange them in rows such that each sphere is in contact with each adjacent one. In that case, one sphere is in contact with the 2 adjacent sphere. What is the coordination number? It is 2. There. Now there is second one. Here it is 2-dimensional packing. I am going to arrange rows one above the other. Okay, such that each sphere is in contact with 4 neighbors. So here the coordination number is 4. Okay, and each sphere is, since it is touching one above the other, I'll be getting a square shape. So this is called as square close packed 2 dimension, packing in 2 dimension. Now when the particles in the next row are placed in the depression between the particles of the first row, then they are vertically aligned with the first row. This type is called as hexagonal packing, and this is called as hexagonal close packing. Yeah, children, this is square close packing where I have arranged one row above the other. Whatever I have explained, I am just showing you in the picture. See, this is row 1, that is A, row 2A, because identical. This is row 3A, this is row 4A. Now see one sphere is in contact with 4 adjacent neighbors, correct? 1, 2, 3, 4. So it is in contact with 4 neighboring sphere. What is the coordination number for this, children? It is 4. And what is the shape of the sphere? It is in the form of a square shape, so it is called as square close packing. Now I have moved to the next topic. This is hexagonal close packing. I have kept row 1. Row 1 is A. I am going to call row 2 as B. Why, children? Because it is not aligned like this. It is not aligned like this. But you know how it is aligned? The depression between 2 spheres has got 1 sphere. Depression between 2 spheres has got 1 sphere. So I have kept A. On top of it, I have kept B row. How I have placed B row? Such that the depression of the A is occupied by the sphere of B. Similarly, the depression of B is occupied by A and A depression is occupied by B. So in this case, the rows are not similar. That's the reason why they have named as AB, AB. Clear? In this, see what is the shape here you are getting, children? I am getting a hexagonal shape. Hexagon 6, right? 1, 2, 3, 4, 5, 6. So I have got when these spheres are adjacent together, when they are close to their neighbors, they are getting the shape of a hexagon. So I am going to call them as hexagonal close packed structure in 2 dimension. Now moving back to theory, children. I told you the spheres in first row is A type, the one in the second row is different and it should be called as B. And when the third row is placed adjacent to the second in a staggered manner such that the spheres are aligned with those of the first layer. Hence this layer is also type A. So the spheres are similarly placed like 1, 2, 3 and 4. See, and hence this arrangement is called as AB type. And in this case there is some empty places and those empty places are called as voids. Children, can you see the empty places where you are not occupied? Even we have empty places in square close packing too. In square close packing you have more empty spaces. The voids are bigger in size. While in hexagonal close packing also we too have voids which are smaller in size compared to square close packing. Okay. Now we have seen single dimension, we have seen, and then we have seen 2 dimension. In 2 dimension I got 2 structures. One is hexagonal close packing, another one is square close packing. Moving to the third way of packaging, that is 3 dimensional packaging. Okay, 3 dimensional close packaging from 2 dimensional square close packed layers. See, I am going to place the second square close packed layer above the first. We follow the same rule that was followed when one row was placed adjacent to the other. How I have placed? I have placed the second layer over the first layer such that spheres of the upper layer are exactly above the first layer. In this arrangement, spheres of both the layers perpendicularly align to each other either horizontally or vertically. Correct? So what is 3-dimensional packing? I have arranged layer 1 and layer 2 such that each layered particles are perfectly aligning together either horizontally and vertically. They do both. Horizontal alignment and vertical alignment is happening when you place 2 rows exactly which are similar. Now, when we place more layers one above the other, if the arrangement of sphere in the first layer is called A type, and all the layers have the same arrangement, then this lattice is called as AA. Hope you all remember this, whatever we have explained before. The type pattern, so this is AA type pattern. Now what happens in hexagonal close packing, children? We don't have AAA type pattern, but we have AB pattern. Yeah. The lattice which is generated is simple cubic lattice and its unit cell is called as primitive unit cell. And whatever the lattice I have obtained, this is called as crystal lattice. See, this is the 3-dimensional close packing from 2-dimensional hexagonal closed packed layers. Now you see the 3-dimensional closed packed generate. How you will generate this? By placing layers one over the other such that they are perfectly aligning on them. See, they are not occupying the depression of the first layer. In hexagonal closed packing, what did I tell you? The depression of the layers is occupied by the spheres of the second layer. That doesn't happen here. This is a simple packing, just keeping layer 1, then on that layer 2, layer 3, layer 4, keeping the layers one above the other. I will be getting a square packed structure and this is called as crystal lattice and each unit cell is called as 1 cubic unit cell. Okay. Now placing the second layer over the first layer. This is like hexagonal closed packing. I am going to place the second layer such that they are going to occupy the depression. And what is this type, children? This type is called as AB type. Hope you all remember. See, whenever the sphere of the second layer is placed above the void of the first layer, a tetragonal void is cleared. I am going to call this as a tetragonal void because you know how many? 1, 2, 3, 4. 4 voids. I mean 4 spheres are going to form a void. So this is called as tetragonal void. And these, when you arrange them, you will be getting a tetragon. When the corners of the 4 spheres are joined, you will be getting a tetragon. they have been marked as T. Yeah. Can you see the structure, whether it is close to you, whether you are able to see the structure T, children? Will you be able to make out T from here? Yeah. See, as I told you, yeah, as I told you, I have arranged layer 1 and I have arranged layer 2, and you know, tetragonal voids are formed when you join that spheres, when they are formed between 4 of the, see, 1, 2, 3, 4. 4 spheres forming a void is tetragonal void. This is called as tetragonal void. You have to remember only two way: packing in one dimension, clear. Packing in two dimension, we have seen a square closed structure and hexagonal closed packed structure. Then in 3 dimension, we have seen tetragonal voids. Yes, no, children? Packing the second layer over the first layer, I have obtained tetragonal void. So when you join the center of the 4 spheres, you will be getting a regular tetragon. Now, in other places, the tetragonal voids in the second layer are above the triangular voids in the first layer, and the triangular spheres shapes of these do not overlap. One of them have an apex of triangle pointing upwards and the other will be pointing downwards. These voids are marked as O. Yeah. See, the tetragonal voids are placed above the trigonal voids. Trigonal voids are formed by means of 2 spheres, adjacent 2 spheres. Neighboring 3 spheres will be forming a trigonal void. They form a trigonal void in such a way such that the triangular shapes of these do not overlap. And one has an apex, one will be pointing upwards and other will be pointing downwards, and those voids are marked as O here. Now, these voids are surrounded by means of 6 spheres and they are called as octahedral voids. Clear, children? See, there is no any direct correlation. You should not get confused between octahedral void and the tetrahedral void. Octahedral void is surrounded by 6 spheres. And what about tetrahedral void? It will be surrounded by 3 spheres. When you talk literally, your tetragonal void is surrounded by means of 3 spheres. Yes, no, children? And what about octahedral voids? They are surrounded by means of 6 spheres. The number of these 2 types of void depend upon the number of CPP. It depends upon number of closed packed spheres. See, the number of closed packed spheres, let it be represented by the term n. What is this? The number of closed packed spheres is represented by n. The number of octahedral voids generated is equal to n. The number of tetrahedral voids generated should be 2n. In tetrahedral voids, you have 3 adjacent neighboring spheres. In octahedral voids, you have how many? You have 6 spheres. You have 6 spheres. And if octahedral void is represented by n, while your tetrahedral void is represented by 2n. Moving to the next slide. Yeah, this is an example for this picture will be telling you the clear-cut idea about tetrahedral and octahedral voids. Wherever O is there, that is called as octahedral voids. Octahedral voids are surrounded by means of 6 spheres. Yes, no, children? Yeah. 1, 2, 3, 4, 5, 6. Octahedral voids are surrounded by means of 6 spheres, while tetrahedral voids are surrounded by means of 1, 2 and 3 spheres. Yes. I hope you are all able to see even the backward structures, because for octahedral void there is no clear-cut picture. You have to imagine by arranging the rows of ball one above the other, such that in the depression lies your second layer's sphere. Yeah. See, this is tetrahedral hole. Yeah, this is also giving you a clear-cut example. Tetrahedral hole where 1, 2, 3 on top you have 4th hole. Yes, children. And what about octahedral hole? You have already 3 spheres, 1, 2, 3 on above it. See, blue color is showing you. Blue color. Can you see the blue color spheres? 1, 2, 3, which in turn is surrounded by a pink color sphere. 1, 2, 3. So 3 plus 3 is 6, right? I told you octahedral void is surrounded by 6 spheres. Yeah, that is true. 6 spheres it is surrounded by. And what did I told you for tetrahedral void? Tetrahedral void is generated by means of 3 spheres. On top of it, it will be stacked by the other one. So in hexagonal close packing and closed packing, cubic close packing methods of stacking, the sphere is in contact with the 6 other spheres in its own layer. It directly touches 3 spheres in the layer above and 3 spheres in the layer below. So these spheres are called, that is, it has got 12 neighbors now. Okay, 6 spheres in the top, 6 spheres in the bottom. So it has got 12 neighbors. The number of nearest neighbor in a packing is called as coordination number. In close packing arrangement, that is in hexagonal close packing and cubic close packing, each sphere will be having a coordination number of 12. Yes, no children? We have already seen about the coordination number. The closest neighbors will be giving you the coordination number. Now, this is packaging the third layer over the second layer. Yeah, see the picture. A layer and B is occupying the depression of A, and this is again A layer and B layer. This is AB arrangement. I am going to pack the third layer over the second layer, covering the tetrahedral void. See, when a tetrahedral void will be generated, when 3 neighbors join, when 3 neighbors touch each other, I will be getting tetrahedral void. Now I am going to cover the tetrahedral void. See, the tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layer will be exactly aligned with the first layer. So the pattern of the sphere is repeated and I will be getting a pattern AB. This structure is called as hexagonal closed packed structure. This sort of arranging the atoms in many materials like magnesium and zinc. So this is how the materials are joined in metals like magnesium and zinc. Whatever we have explained before, this is very simple picture of placing the third layer over the second layer. This is what I have told you in the before picture. I am going to close the trigonal void with the third layer. Okay. Yeah, covering the octahedral voids. Okay. Now see children, tetrahedral void by means of 3 adjacent sphere and octahedral void by means of 6. Blue color one, the dark blue which is in the down layer, and I have closed it with another 2. This is octahedral void and this is tetrahedral void. Now I am going to cover the octahedral void. The third layer should be placed above the second layer in such a way such that the spheres cover the octahedral voids. When you place them in this layer, the spheres of the third layer is not aligned with the first layer. So this arrangement is called as C-type. Okay. Till now we have seen about only 2 types of arrangement, A type or AB type. Here what happens when I am making an attempt to close the octahedral void in such a way, then my third layer cannot be aligned with that of the first layer. It cannot be aligned with the first or the second layer. So this arrangement is called as C type. Now children, see A type, I have 3. I am going to close this 3 with means of B. I have closed with B. Now when I am going to bring the row 3, that is row C or A, B, C. When I am going to close the octahedral void which is created by A and B layer, I am trying to close it with the layer C. The layer C will not align exactly with either B nor with A. This is completely different from A and B. So here comes ABC arrangement. So here comes your ABC arrangement. Now I am going to place the fourth layer. Your fourth layer is nothing but A. When fourth layer is placed, this sphere will be properly aligned with the sphere A. So I am getting the pattern ABC. Clear children? I have layer A, this is A. I have layer B. I have closed the tetrahedral void. Now I have got the octahedral void. Now I have layer C. The layer C will not align with either A or with B. So I have got ABC arrangement. Now I am bringing the fourth layer. The fourth layer is nothing but A. This fourth layer will exactly align with A. So now the pattern follows as ABC. Okay children. Now this structure is called as closed packed structure or face centered cubic closed structure, that is CCP or FCC. What is CCP? Cubic closed packed structure, or what is FCP? Face centered cubic closed packing. Which metal is going to follow this attempt? I mean this kind of arrangement. Metals like silver and copper will be aligned in this arrangement. Okay, metals like silver and copper will be aligned here. Okay, now moving to packing efficiency. What is packing efficiency? You have a formula, that is volume occupied by all the spheres in a unit cell divided by volume of the unit cell into 100. So what is packing efficiency? What is the total volume of all the spheres present in the unit cell divided with the volume of the unit cell into 100. This is called as packing efficiency. Now, can you see the picture, the small a? What is small a? Small a is the edge length of the unit cell and r is the radius of the sphere. The spheres are touching each other, so the radius will be 2r. Okay. What is the radius of sphere 1? It is r. It is going to touch, these spheres are touching each other, so what is the radius? It is 2r. And what is a? It is nothing but the length of, edge length of the unit cell. How many number of spheres per unit cell? This already we have told you. Number of atoms present in unit cell will be 8. So 1/8 will be occupied. 1/8 will be shared by one unit cell. So 1/8 into 8 is equal to 1. That is, we have seen a number of atoms present in unit cell. 1, 2, 3, we got the answer. Now what is the volume of the sphere? It is 4/3 pi r cube. What is the volume of the cube? It is a cube. Since I have taken two spheres, it is 2r cube, which is nothing but 8r cube. Now the fraction of the sphere occupied is equal to, I have taken one fraction, so 1/3 pi r cube divided by 8r cube, which is equal to this much. So percentage of the how much percentage this has occupied? It is 52.4%. Okay, kindly try to remember this formula. With this we'll stop. I'll be explaining about the packing efficiency in case of body centered and face centered structure, children. Thank you.